In this video, we will give a more system perspective of the voltage control and reactive power in the grid system. Up to the left here, we can see a PV curve. It gives a relationship with the voltage and the reactive power in a specific node. So this we call the PV curves, and it's related to the node location, like here, for example, here. So it shows then how the voltage will relate with the constant power, for example, on the load, with at different power factors. So from the compensation and how it will affect the voltage profile. Typically, we want to have a flat line voltage profile. So if you see here, you can see a profile going here. So if we start to increase the load, then we can get like a really lowering of the voltage at that node. Here you can see now we're going down in voltage. Then we can increase compensation, and we can see we can actually a possibility. We can at the same load now we have increased the voltage, and we're keeping them more flat here. And vice versa when you're taking the inductive part. So this is like showing, this is Norwegian, sorry, but it's overcompensation. I'm giving us own video to how we can develop this PV curve by equations. So we typically have an inductive shunt compensation at light load, and we can have, when you're talking about shunt, we do compensation in parallel. So we can have inductive L, or we can have a capacitor QC or XC. Let's keep QL then. Depending on if you have a light load or heavy load. So heavy load, you need more capacitance than the shunt. Also is by doing maximum power transfer. By actually then do this type of compensation, we can increase the possibility for transfer. So we're saying that the capacity series compensation increases maximum power transfer, and now we're talking about series compensation. So that means that we are putting something in the series here within the line to do compensation. And capacitive shunt compensation has only a small effect when it comes to this. So when you talk about power transfer, then it's much what you do in series in the line here. So if the reactance goes up and down, this is something you have been looking at in load flow. When we're talking about shunt, is it here at the node, and we're talking in the parallel with the load. So here you know this power triangle SPQL, and then we of course know that QC has an opposite effect. So this is the main idea when we're talking about shunt. I will come back to this a little bit later. So what are the reactive power control objectives, you can say? Yeah, that is one thing is that it's to keep then the voltage at all terminals within acceptable limits. And what are acceptable limits? Typically it's between the 0.9 and 1.1, or maybe less, 0.95 to 1.05. But you need to keep it in limits. Other objective is to enhance system stability in order to maximize utilization of the transmission system. So you can also see that we can use the reactive power to actually stabilize the system, grid system. And also reduce reactive power flow, reduce losses by doing this. So this is, I will say, 3 main control objectives of the reactive power. So remember that like transmission line have a XR ratio. So depending on type of line, and also for example, if you see that you have, when you increase the voltage, you can see here, you have a you see the reactance will change. So you get a higher X per unit when you get lower here in the voltage level. However, when you're working on distribution system level, then of course the resistance will increase. But here you can see the X to R ratio typically in this voltage levels here. So what are the problems and challenges related to this? I can give you an overview here. One is that you have a many number of loads, terminals, and systems. So it's to keep track of all the loads. Many generator units. We also know that reactive power requirements varies with load. And also transportation, I just mentioned, reactive power is not desired and inefficient. It takes the space of the active power flow. Reactive power must be controlled by distributed systems. So we're saying that it's like it's not a power you are sending in a long distance. This is like a short distance power transfer, and that is a contradiction to the active power. So that's why you typically need to control this reactive power in distributed system out close to where it's actually needed. One important thing that really affects the reactive power demand is the load characteristic, both what you call a static and dynamic characteristic. When you talk about static, we are using so-called what you call a SIP model. So then we are specifying how much constant impedance, how much constant current, and how much constant power are there in the load. So typically when you're doing a load flow system simulation on the transmission perspective, then you typically don't know further down than actually the distribution transformer. So then you have to put up like a kind of model for the load. So this is not like a part of the course, but you'll probably come back to when you're working with stability. But you should know that you have something with the load characteristic to do, and we call it the SIP model. And we're making this model with some kind of constants. So you can see, for example, if you have battery charger, you can using an alpha beta, like here, to actually represent the effect of how the voltage will vary. So you can see here they're putting like a linear relationship and then a quadratic, depending on what type of load it is. And you can also see here is here's the alpha and beta. So you typically have battery charger, you using 2.59 here and 4.06 here for the reactive power. So it's very sensitive then to the change of voltage actually. For the dynamic on the right hand side here, we can typically have like a load, a motor is going out of the system, and you can have a motor load recovery after voltage drop. And that depend on what kind of torque model and how type of model motor. But typically when you have a drop in voltage, the motors will be shutted off the grid system. It can be. So yeah, but this is still, we will not focus much on the dynamic load and so on. It's probably common in all the courses, but the load characteristic is important. That's the main thing for the voltage control of the system. Here's a nice overview of the what all the components in the grid system are actually power producer of reactive power and what is actually consuming reactive power. And we know that the generator, they can both produce and absorb, both in overexcited and underexcited mode. Overhead lines at load load will produce actually, and it will absorb at high load. Now to the left I have drawn a figure, and this is a concept that's called surge impedance load. SIL. So just briefly mention it. And if you have a long distance overhead line, like here for 0 to 1500 kilometer, the voltage profile over this line can be looking something as you see here. And if you have voltage on the sending end is higher than V2, we have an inductive nature. And opposite, you can have a capacitance nature. I also put out a small exercise on this, and you also probably seen that in lab, but you can actually with very light low have a high or open in the end. You can have a higher voltage in the receiving than in the sending. This surge impedance load is actually that we have compensated all through the whole line. So we have PR, it's just resistance, equal P surge impedance load. This is a concept you can see when you are working with overhead lines. So we will not use much time, but you can find this in different literature if you want to know more about this. Further, we have cables. They are production. They are producer or reactive power. Transformers is of course have an inductive nature, and you have absorption here. And then we have loads, usually inductive, so it absorbs, harmonic filters, produce, and also if you have line commuter variable speed drives, we will have absorption of reactive power. And of course, compensation devices will have both possibilities. So what kind of methods do we have for the control of voltage and reactive power? And the sources we can say, I noted here, such as generators. And we have shunt capacitors, talk about, and something called rotating condensers, and static VAR compensators, SVC systems. And rotating condenser is typically like a generator without the turbine, so you are just producing reactive power in the grid and control the voltage. Reactive sinks can be also rotating condensers, static VAR compensators, and shunt reactors now. So that's a possibility. Other methods is line reactance compensation. You can use so-called fax devices, I'll come back to that, or series capacitors. And also you have the regulating transformers, the tap changers, and boosters. So we have briefly talked about earlier. I just put up this small table also, just to highlight just a small thing. But of course, like a generator, it has a speed of response when it comes to voltage control. It's fast. So here you can see you can divide it in voltage support and of course if it's expensive to use it actually. And we're saying that the ability, excellent additional short-term capacity for the generator, often low availability, and operating an opportunity can be high cost because you probably have to lower your active power. It can be. So, but one thing I wanted to point out also is that, for example, the capacitor or static VAR, it has a speed that is slow, and it also ability is poor. It drops with voltage and square. That means that even though the voltage in the grid system goes down, we will see that later, we can use the generator to try to keep up the reactive power of the voltage because it has an internal voltage source, you know. However, the capacitors are the passive elements and they just follow the voltage in square. That's important. I will just briefly also talk about what we call FACTS and what we call flexible AC transmission systems. Here is an overview from Siemens. It's actually a very nice table that we work a lot with, but I will just focus now on the voltage control, shunt compensation here. And what we can see here, we can see an impact on system performance. And here is load flow, stability, and voltage quality. When we are doing a compensation using devices such as the fixed series, thyristor protector series compensation, thyristor control series compensation, then we have a lot of impact on stability properties of the system, but not so much on voltage quality. However, when it comes to the shunt, not the series, then we such as SVC systems, STATCOM systems, then we have lesser impact on the stability, no impact on load flow, almost, but a high impact on the voltage quality. When it comes to load flow control, you can use the H voltage DC back-to-back systems, or what they call unified power flow controller. These are of course very expensive equipment, but you see this is has a full score on all of the 3 system performance criteria. But what they should remember is this shunt system will have a high effect on the voltage quality. Let's look at one case study from the US on dynamic voltage control. So what they wanted to find out here, this is from American Utility, and they wanted to find out that should we, here we can see like a sketch of the grid system. Should we put reactive power compensation central here, or should we distribute it like this? And when we do, so they tested then this 1 times 500 MVAR SVC in central location, 1 times 250 MVAR STATCOM in central, or 3 times 150 MVAR STATCOM distributed. That was they wanted to test. And we could see that, so we have a fault in the system, and all of these 3 systems brings the voltage back. So this is, if you don't have any compensation, you will have a fall in the voltage, severe fall. But when you're using these 3 compensation techniques, we can bring the voltage back. But the question is how much reactive power was needed to do that. We should remember that the characteristic typically for like the SVC systems, like this 150, is that the amount of reactive power they can provide drops with voltage. So it has this V characteristic. However, the STATCOM can actually produce full all the time reactive power until, of course, in a limitation in the minimum value. So to the right here, you can see that the SVC MVAR output use this amount of reactive power. However, STATCOM used only, like this, we're using 350, 60 or something here. However, with the STATCOM, they only use 250. So they wanted to use the voltage source converter technology to utilize, decided to install 3 times 125 MVAR STATCOM distributed. That was their decision on this case. So shunt reactors can be used then to compensate line and cable capacitance when you have a light loaded situation, as I talked about previously. It can be also required for extra high voltage transformer transmission systems, such larger than, for example, 200 km. And it typically are switchable disconnection at large load. So, and this is how you can put them in your system, to a weak system, to a strong system, in such a manner. For the shunt capacitor, then they are used to supply reactive power and boost local voltage. And that was, as I mentioned a little bit earlier also, that we typically have to do the compensation locally. Advantage is that it has low cost, it has flexibility of installation operation, and can be used at all levels down to the end user side. So here you can see a sending side and a load side, and you then do a shunt capacitor at the load side. The disadvantage I already mentioned in the SVC system is that reactive power output proportional to the voltage in square. It can be used for power factor control and feeder voltage control. There are exercises to this topic we have this week, where you have 5 lines, such like this, and then we drop out 1 line at a time to see what that does with the possibility for both active and reactive accessible for on the receiving side here. So you have a 5000 megawatt here in the receiving side, and then you have a generator or a grid system on the left hand side with 400 kV here. You have 5 lines, 200 kilometers. So what you see on the right hand side here is what they call a chin curves. So you get a relationship between the reactive power and the voltage. Let's see if I can get this up a little bit so you can maybe see it. Yeah. So spending is voltage, just in Norwegian. Sorry about that. So you can see that this is n minus 0, n minus 1, n minus 2, n minus 3. So here, of course, n is equal to 5. It's 5 lines. Let's show the expression for the chin curves before we look more on the curves. So we have this system as you have here, and reactive power compensation, shunt compensation. So from the lossless power flow equations, we have this here for active power, and now reactive power. And you can see we have putting the QC into this power flow equation. We can then take and express them different way. Let's see, we have expressed as first one xp minus ep sine delta. The other one xq minus qc minus plus ev cos delta. Okay, let's take it further. Then we try to eliminate the transfer angle. Eliminate transfer angle. This we do by quadratic. Let's see, we can then take e squared v squared equal squared p squared. Let's take the other one. E squared v squared delta. Like this. And then we put it together and we get E like this, I think, because now sine squared and then cos squared becomes 1 removed, and then we have e squared v squared, yes, x squared p here, yeah, that's correct. And then we can set the value for that we are p and q, and can solve this equation for then the amount of QC, the reactive power compensation. So let's do that. We will get the following expression. See QC as a function of V, that was the chin curve, Q plus V squared X minus square root of EV X squared minus P squared. This is the expression for the chin curve. So of course, if you have a constant power, and also constant E. Let's see if I do constant P, constant E, and also Q is given from the load side. And in the exercise, of course, when the lines the total drops off and you get n minus 1, n minus 2, then we will have a change in the total x of the transfer system. That's important. So let's look closer to the thin curve. If you see on the blue curve here now, firstly, and then if you want to have 400 voltage now with 5000 megawatts here, that means that if you don't do anything compensation here now, that means that you will have a drop in your voltage here. So you will follow that curve, because that's the characteristic curve. So then if you want to keep 400 voltage for this, then that means you have to put in reactive power to that amount, as you can see here, to raise the voltage up here. If we have a loss of line, then it follows a new curve. Now, one line out, we have this red curve here. So at the same way, now we have to have even more reactive power in to bring it back to 400 volt. And then we can continue n minus 2, for example, here. We have to actually have even more, and so on. So this can give an indication then, if you want the voltage, we can know how much reactive power we should compensate with to actually keep your voltage or as a flat profile. Let's talk a little bit more on series capacitors. So they are used to compensate the line inductive reactance. So you can put it in this fashion. This is a feature that can show how you can use it to compensate the of the line total reactance. Use it to reduce the transfer reactance, increase maximum transfer power, and reduce effective reactive loss. The advantage compared to reactive shunt just talked about is that the reactive power production increases with increased power transfer. So more transfer power, more increase in reactive power production. It can respond immediately to load changes, so it's in series, and you can typically use it on distribution feeders such as arc furnaces, other fluctuating loads, and modification of load sharing between lines. This is not like the core thing you should know, but I put it up so you can have an overview of it. We can use this here capacitor for stability improvement of the grid system. Here's an example of in Brazil, 500 kilovolt AC long distance transmission. And they use then this series compensation. Here they're putting in each line, this is a 1000 kilometer line, and it inserted a twisted control serial capacitor here, twisted control serial capacitor, and 5 fixed serial capacitors here on the transmission line. So let's see on the first picture here, we have a disturbance in your system, and this is the total impedance, this here. And this here you can see the oscillation, the slow oscillation of the power in your system. So there are no TCSC, and the system is unstable. And the line trips actually after 70 seconds. When we're working with one, and then we go on here, one twisted control series capacitor, you can see how the impedance tries to compensate now. It works. And you can see it means going to stable, and you will have a system stable. However, if you are using two of them in each line, you can see that it's much faster. It's now will stabilize your system. So in that way, you can use it for stability properties. This is of course another course, so and we focus on the voltage control, but then you know how we use them. I will finally now talk about this blackout or power shutdown that can happen actually in your system, and an example of that. So we're thinking that okay, we lose our power maybe in 1 hour or something in your home, but imagine that the whole region are gone, the whole so the whole school, your house, actually the water supply, you cannot get water in your sink and so on. And if this is in winter, you have can be a catastrophic, of course. And we just take it for granted that we have the power supplied all the time. But we could imagine such a scenario actually. One example of this is the in 2003 in the US. So they call it the day the lights went out actually. So we know that the power balance is extremely important in electricity, and here they had some reactive power supply problems. Let's see. So this is number one, reactive power supply problems in this area here. And you can see the black area here, so they call it the blackout in North America, seen from space. So if the balance criteria are not met, we know the complete system shuts down. So you don't lose a little bit, you lose everything of them. You have real-time continuously analysis software that were not inoperative, so we had a problem. And the first major event was the outage of a large generator due to overexcitation. So now the system, the lines demanded a lot of reactive power to compensate. Or I think it was a line that went out. You need to try to transmit it over a long distance, and then another line also goes out. And this is the second fault. And the critical event leading to widespread cascading, as we call it. So then it took time to bring it up, and it was when big cities get out of the dark. You can look on YouTube and see example on this 2003 event. And so this is called what you call a long-term voltage stability scenario. Okay, let me just do one thing here now. Let's see. Now we probably can see it. We have, yeah, it's a little bit related to this example in your exercise, but here's again 5 transmission lines, and we have a generator on the right hand side, generator 3, that are providing reactive power to the local systems here. So this is the generator providing reactive power for local and the load. Then we have and then we have active power is actually transferred over the lines here. So the main, so it's like a production site transferring it to a load side. When you need more reactive power from the generator, you have a higher temperature in the machine. So it's a limitation. As I said, only example from 2003. It's a maximum excitation level that you can do, then it starts to ramp down the excitation. So you have a fault, one of the transmission lines goes out, and the active power has now to be transmitted on the 4 others. So you have an increase in loadings on these 4. So they are more stressed. Also the reactance increases now, the total electric distance between this bus here, bus 7 and bus 6. And all of this also demands more reactive power to for the losses. And also the Q increases a lot to compensate both to the lines and also to the load side. Then we have a step-up transformer that starts to step up the voltage on this side. When it steps up the voltage, because it wants to keep the voltage at the for example, for the motors and so on, then it reduces the reactive power. Now voltage on this side, that means it further demands more Q here to increase the voltage. That stresses this even more, and then you're getting this warning, ramp down, decrease excitation. So it starts to ramp down, and then when it ramps down, then it needs more Q transported from this side to keep up the voltage. And then this remote generator also starts to ramp up. It comes and then we are stepping toward a disaster or a blackout of the system. So what is actually happening is that this curve, as we had talked about now several times, you are then stepping out of disaster, out on this instability maximum point, and you drop out, and you are coming for a blackout here. So the whole system collapses in this fashion. So this is the final slide on this presentation. I'll try to give you overall the system and how it can affect the long-term voltage stability in this video.